And our next speaker will be Riccardo Arcodia, who's currently a Einstein Fellow at MIT.
Thanks everyone for being here. Thanks String for the beautiful introduction. I'm gonna focus now mostly on the eROSITA QPEs, the two that are public and the two that I am in the process of publishing, and the news that they're bringing to the table. And Join, I've used a couple of your plots, and I'm showing that these correlations are now in place with the new QPEs. I'm sorry about that. It's a plot that I've made yesterday on the train, so I didn't have time to tell you, but it doesn't really matter. The whole point is that every few months, what you think you know about QPEs changes. So that's quite fun to be part of this. Okay. Do you work? You don't work. Yes. Okay. So I'll briefly tell you how I'm finding QPEs with eROSITA. Just I think it's because it's relevant for the discussion later, and maybe some of you have more ideas on what to do. Just as a brief introduction on eROSITA. So we've learned from Join that the QPEs can only be found by in X-rays. Well, at least that's what we think at the moment. And in summer 2019, eROSITA was launched, and that's pretty much how I got involved into this. Just as a very short summary, eROSITA sensitivity. This is how good your instrument is in collecting photons in a given amount of time as a function of energy. eROSITA is in red, and it's right there at the top, together with, for instance, XMM Newton. So these telescopes are made for collecting photons at the expense of angular resolution. And eROSITA's field of view is actually much larger than XMM Newton and Chandra's. So the so-called grasp, so how many photons you get in a given amount of time in a given amount of area, is pretty large. And the survey, the eROSITA was designed to perform surveys of the whole sky. It's at L2, the Lagrangian point opposite to the Earth, and it was rotating its field of view around the ecliptic plane, performing all sky surveys, and it would finish one every 6 months. So it takes 6 months to scan the whole sky in X-rays. And to date, there are 4 all-sky surveys completed, plus a little bit of the 5th one. And that's the data set I've been using to find QPEs. But the point is that this is not just a single image. It's rather a stop-motion animation. So basically, each image is compiled by shorter images of 40 seconds, taken a few hours, rather than a single passage. So for instance, imagine there is a source which is undergoing QPEs in the sky. eROSITA passes on it one time and it finds a detection. Then 4 hours later, there's nothing, maybe nothing again, something else has popped up at the same location as the field of view moves further out, then nothing again. This is the sketch we had in mind when QPEs were discovered. We had eROSITA. We were like, okay, let's see if we find QPEs in the data stream. But you clearly, if you see this sort of light curve, well, sure, you look that is coming from a galaxy, but you need follow-up to confirm this candidate as a QPE. And so during the first, actually during my PhD, I was looking for these sort of patterns coming blindly from extragalactic sources in the sky. And we found 2 more QPEs, and they look like this in the eROSITA data stream. So as I said, non-detection, 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 bright detection, and so on, with the 2 bright states at least to find it as a source that was varying with some sort of recurrence. They were both coming from 2 galaxies, and we confirmed them with follow-up with NICER on the left and XMM Newton on the right. At the time, we found the QPE with the longest recurrence period and the shortest recurrence period. This is about 10-11 days of data with NICER. Just to give you an idea, it's a fairly expensive observation to confirm this one candidate. And this is 1 orbit of XMM Newton, so of the order of 20-30 hours, which is also fairly expensive to get. So the point I want to make here is that, sure, we have perhaps a bunch of candidates which are obvious. For instance, these 2 showed the higher significance in variability. There are potentially tens or hundreds of these sources if you put your significance or variability to be lower, but you can't follow tens or 100 sources, but they all look the same. So my point is like tier 2 of these variable sources in the eROSITA data stream is probably too complex to follow up in a blind way. So we have to find some other way at some point in the future, which I'll think about it in the next year, I think. But anyway, as we have now 4 or 5 all-sky survey per source, one could try to find candidates which flared once per survey, but in more than one survey. So this kind of extends, since QPs last for years, you can do that. You have 4 or 5 images. If you see a source that flares once in an image and once in another image, half a year to a year and a half after that, it could still be a QP candidate. And that's how we found eROQP3. You see now on the left a collection of 5 light curves from eROSITA, eROS 1, eROS 2, 3, 4, 5. And you see 2 interesting things. Well, we kind of detected a potential bright phase in every survey. It triggered my algorithm in these 3 searches. This is low significance, and this is also low significance, but just because the question submission is brighter. And I'll come back to that. This is one other source for which the question submission has decayed. You can see, if you're next to someone, you can see it by eye. This is count rate and not even scaled in the same way on the y-axis, but you can see that basically the gray line is background and the source has slowly become undetected when it's not flaring in the eROSITA data. It was coming from this very compact galaxy, but this wasn't a requirement for me to consider it a QP candidate. I first look just at the variability, then I look it's extragalactic or not. And by chance happens to be another small compact galaxy. And this is the confirmation XM Newton. There is also some nicer data that I'm trying to work on with Join. This is now 2 orbits with XMM. Again, very, very expensive, and you can only get 3 bursts using a lot of time with XMM Newton. These are 2 QPs spaced by 20 hours, and in the second observation, only one was found, but using the recurrence of 20 hours, it could have happened right before and right after this observation. With NICER, we saw at least 2 bursts separated by 17 hours, and we're trying to dig more into the noise because these are faint. This peak is at around the detection limit of NICER, so this source is quite hard to follow up. Another way that we
peak luminosity and
I'll come back to that. Yeah, peak luminosity is about a few 10 to the 41, so this is the faintest one discovered to date. But sorry, what I meant faint in this particular moment was also simply just count rate faint in terms of the NICER detectability. Yeah, so this is the faintest one discovered so far in terms of luminosity instead. Another way that I've barely started exploring, so I thought, okay, this is now a bit less of a blind search. Until eROQP3, you just look for amplitude variability that repeats, and then you go for follow-up. In this case, we thought, okay, let's look at the source that only flared once in the eROSITA data stream ever. This could be also GRPs or whatever, neutron transmeasure, a lot of things that we don't understand even. But looking at where it comes from, it was still a compact galaxy, and this was very sorry, now with the real data, this was fairly high significance. This galaxy wasn't detected for 3 surveys and detected in the 4th survey only in one of the scans. It was coming from a fairly compact galaxy. We thought, okay, let's give it a chance, and we got some data on it. And that's now eROQP4. So this is the NICER light curve, about 5 days of data with some bursts that repeat every 10-15 hours. This is XMM, again, 30 hours, so the longest observation you can take with XMM. And still, it only gave us 3 bursts. Separation of 10 hours and 15 hours. You can already see, the well-behaved QPs are not necessarily common, if we want to call them well-behaved in terms of regularity of the separations and on the amplitudes. This is potentially varying in terms of amplitude and recurrences. And this is not something, it was something I was seeing before, but it seemed to be like, this seems to be the normal behavior rather than the regular one. And yeah, so I will continue looking for sources like this now. It's a bit of a less blind search because I in order to trigger follow-up on these and not waste anybody's time, I will probably look for galaxies that look like the ones that I found QPEs in so far. But I think there is of the order of maybe 2 per survey of sources that look like this. So maybe another 1 or 2 could be found in this way, but it's hard to say at the moment. I'll work on this over the summer.
Is each survey looking at a different part of the sky?
No, it's the same part of the sky, but you can consider them like an independent sampling of the light curve, if that makes sense. So you have something like that evolves with a duty cycle of the order of 5–10%, and we have our points, like handful of points every 4 hours. You can easily miss, and it's actually, for instance, what might have happened here. We've missed these QPEs for 3 surveys, and only the 1 among these 9 points. These are 40 seconds exposures. So yeah, surely we are missing out on a lot of sources. There's no doubt. Actually, that's a relevant point for this plot, because if I want to convert these observations to intrinsic rates, I have to plug in our efficient time into detecting them, and it's something that I can quantify. Now, this plot, I made this plot after eROSITA 1 and 2. It's also probably relevant to keep it that way because they were found in the same exact way, with the same exact algorithm. I've changed it a little bit for eROSITA 3 and 4, and also I plugged in kind of my own judgment in it, which is hard to quantify in a number for the efficiency. But in this way, what I basically did was to simulate the efficiency of detecting the existing light curve with eROSITA, so that I can give you intrinsic rates. Now, this is a plot of in terms of megaparsec cubes. This is a plot in terms of galaxy density using galaxies of stellar masses of 10 to the 9. This is not a formation rate. You don't see the time variable here because QPEs outlast my survey. I can only give you the number of sources that are emitting QPEs at any time. And this number is, if you sum or whatever, integrate this curve, about 1 every 10 to the 5 galaxies of this mass is undergoing QPEs at any time. If you plug in a lifetime of 100 years as an example, you get a formation rate of 10 to the -7 per galaxy per year. So this is about 1,000 times smaller than the formation rate of TDs, for instance. But for instance, the fact that they last 100 times and they're not one-off events, their detectability can be kind of comparable in a survey. Maybe a factor of 10 less QPEs than TDs. It depends on the type of survey that you want to design. But anyway, this tells you essentially, well, fundamentally, if these are MRIs, this is the first ever observational lower limit to MRI rates, which is quite powerful for LISA, regardless on the fact that sources with QPEs will ever be detected by LISA. This is some of the MRIs, so it's a lower limit of the MRIs. I will update this plot now when I publish eROSITA 3 and 4, but I think this ballpark is probably going to remain the same with the usual decks of uncertainties for the volumetric rates. Yeah, so this doesn't tell you anything about the TD plus QP connection, right? This is an independent thing. Also, in the context of your models, you just need a TD to shine gas on this QP MRI. So there's no other way I would relate these rates together. But it's actually the argument that we were making at some point, which is probably you're going to talk about it tomorrow. In the latest phases of the MRI, this is such a long evolution driven by gravitational wave emission that statistically in this galaxy you have a TD every 10 to the 4 years. So they will find, these MRIs will find statistically several TDs during his lifetime.
The argument is that the in-spiral rate of a quasi-circular MRI through the range of radii where a TD would deposit gas is longer than the interval between TDs. So if you have, so every MRI that's kind of migrating in gets hit by a TD in its lifetime.
Yeah, these galaxies have pretty high rates of TD.
And so, yeah, these numbers make sense in that regards. If you said that the true MRI rate was a factor of 100, as you say, less. than the TD rate or something like that, then, the numbers kind of work out. If it survives for 100 years, as you said,
Yeah.
tens of years or something. Yeah.
And depending upon the mass ratio, couldn't the existence of the emery actually boost the TDE rate? So, I mean, it's connected in the other direction as well.
Right. So if you had well, that's Itai can answer, but if you have a galaxy which is enhanced in TDEs, and it's the same mechanism as you say is enhancing. So if you have a galaxy that is producing an abnormally large number of TDEs, in general that may also lead to. I mean, it depends. The emerys and TDEs are seeded from different parts of the nucleus, right? So it doesn't necessarily imply that if you have a mechanism to enhance TD rates, that will enhance QP rates, but
No, I'm going the other way.
Oh.
I'm saying if you have the emery to begin with, you have the high ratio binary system. Couldn't that boost the likelihood that you have a TDE in that system, that you have a star
So,
that gets disrupted?
so I think in principle, maybe, I mean, right, if your potential is not spherical symmetric, right? Either because you have this, very massive companion to the supermassive black hole. But I think, at least in our
Do we know
model.
the constraints on the relative ratios? I mean, it
So-
could be an intermediate mass black hole
Right,
orbiting a
so-
supermassive black hole,
So
right?
I'll discuss this tomorrow. So in our model, we actually favor a main sequence star. So, it will
Right, no
definitely
way.
not
Right.
have an impact on
Sure.
the overall TDE rate. There are other issues that arise if you try to invoke a massive like an IMBH, partly because then it's an indirect argument, but if QPEs are actually associated with an IMBH, and given the observation or the abundance of them, that would imply that the growth rate of supermassive black hole would be dominated by accretion of these IMBHs simply because of gravitational waving spiral, and we can set constraints on that. So I think there are arguments against a massive IMBH being the source of these QPEs, but I will say that there are also these models that propose that QPEs are somehow related to some either lensing of an accretion disk by a companion or things like that. So the jury is still out.
Right.
At least within the context of the standard emery models, I think that a low mass companion is actually favored, and then I would find it hard to believe that this would enhance the TDE rate. So
Sure, yeah, I think you're right, if it's a main sequence star.
It's
If it's a 10 to the 4th
it's probably not
companion, then.
so the primary is
Brian's comment is actually relevant, right? But if this galaxy is somehow dynamically active, right? Plenty of TDEs because the relaxation rate is high, then this would also enhance the rate at which emeries are formed. So these things come together.
Yeah.
Can I just say, should we let Ricky just finish talk about when we come back to this afterwards? I think you're guilty as well.
I initiated the discussion, to be fair. Yeah.
It's his fault.
So it's fine. But we're changing a little bit topic, so it was fine. So what's new from this is eROSITA QPEs? I'm gonna give you updates on the ones that are public, and I'm gonna tell you what the new ones look like. This is the setup that I'm assuming for now. I'm pretty sure everybody's happy in this room. So it's some sort of orbiting system. Whatever happens here when the orbiter interacts with the disk. At the moment, I'm not caring too much. What type of orbiter, I'm not caring too much. We can fight tomorrow, not today. Okay, as regarding the generic QPE properties, so this is the plot that you showed you in. This is where your QPE 3 and 4 would be. So yeah, so in principle, if this is an emery, so model dependent explanation, and if the QPE duration is given by the some disk properties, the separation by the orbiting object, there's not a really obvious reason to me as to why they should be related, unless they because if this time scale is not a function of the tidal radius, it's just this emery. And for instance, QPE3 has a very long period, but the bursts are a bit shorter. QPE4 is somewhat intermediate, but this sort of scaling relationship doesn't need to apply. By the way, this is a problem for me because implicitly I was assuming this when I was computing my rates, just because I was saying, okay, if I have a peak luminosity, I have a separation, I have a duration-ish with some scatter. But if this is a 3D cube now, I need to kind of find a way to correct the rates, but that's my problem, not yours. In terms of luminosity scalings, I don't think I was too lazy to make the plot, but it's pretty obvious that there isn't one, just because the two ones with the longest evolving timescales are 100 times apart in terms of peak luminosity. So yeah, I'm not going to make this plot. It's probably, there's no scaling relation with peak luminosity at the moment and the timescales. Regarding the optical spectra, so this is in Thomas's paper, used highest quality data with the smaller slits, and he performed accurate continuum compared to what I did when I first discovered the two eROSITA QPEs. This is now eROQP3 with the same spectral quality of my discovery paper. Just to give you an idea what it looks like, you maybe see a faint H alpha if you trust this wiggle, and for instance, not this one. Faint O3, you can subtract the continuum, kind of fit a flux on these lines if you want, and this would look like a star-forming galaxy. But again, you know, the continuum is noisy, the quality is not the best. My point is there isn't a strong AGN in this galaxy either in eROQP3. But then again, a point for discussion is what to do to connect the QPs and the lines using the optical, and the answer is probably not with this spectrum. And in fact, Thomas is also leading now efforts to get IFU data, so spatially resolved spectroscopy in the galaxy and HST data to connect more the properties of the QPs and you know, the fluxes in the lines of the host galaxy compared to these diagnostics, which are, in my mind, they work if you have 100,000 galaxies and you want to split your population in a statistically relevant way. For the single galaxy, I guess they work to some extent. Regarding the stellar mass of eROQP3, it's still fairly low. We can discuss later whether this is an observational bias or not. eROQP4, I was trying to do this yesterday on the train and I failed, but I didn't feed the spectrum yet, but this is what it looks like, identical to the other one. I promise this is a new plot. Slightly higher redshift, very faint H alpha, very faint O3. I still need to subtract the continuum, but it doesn't look like too different from the other ones that I found in eROSITA. Regarding the radio properties of the eROSITA QPEs, they're very elusive. eROQP1, 3, and 4 are undetected. You can see in this plot eROQP3 and 4, the upper limits that they have at 5.5 and 9 gigahertz with APCA. This is work that I'm doing with Adele Goodwin from 13. And eROQP1 is undetected in radio at a level of about 10 microjansky with Meerkat. We tried to have an intense-ish VLA campaign to try and sample one of the X-ray bursts, and it led to non-detections, and the stack non-detection is still 20 microjansky, so nothing to do there. eROQP2 is detected. We are getting more data to kind of try and constrain a spectrum or see whether there is variability. But you know, as it happened for TDs, there isn't any homogeneous answer across the sample, and you know, it's a handful of objects. Nothing to do here. I might need a bit more than that, but it's fine. Okay, what's new on eROQP2? This was one of the first regular ones, and the regularity is not because the period was exact, but because the period was varying in a simple way. It was alternating between a longer and a shorter one, which makes the orbital models quite happy. This is just the evolution of the recurrence time between the bursts over time, and this is how it changed over 2 years. It kind of converged to a single one, and it's also shorter. Now, this is 2 years of gap, so you can't really claim that this is a p-dots, given the fact that we know that these sources might have a modulation in their amplitude. And I've tried to ask for data to constrain the p-dot for 2 years in a row and failed, so I'll try again this year. Given that there are now a lot of memory models out, so it's not something that I was kind of making up. But this is the most well-behaved source, perhaps the only one that has ever had kind of one period. across the now 6+2 candidate sources known. Whereas this is new data, well, not new, but more data that I showed on eROQP1, which was one with the longest recurrence of about a day, a lot of scatter. You can see it by eye in the arrival time. This is XMM data of the same source. And we published last year this sort of complex behavior in which during an observation, there was a clean single burst. A week before, there was a chaos of overlapping bursts in the same amount of time, pretty much. And this is something that we're trying to test with NICER together with Johin. Actually, this is now the 2020-2021 data, which were somewhat well behaved. You can see the peaks by eye. Nice, you don't need to do any fancy timing analysis. You see the bursts, you count them, and we're happy. But then this is what happened in 2023, and yeah, January basically. Data a little bit noisy. We're trying. Johin is putting a lot of work into this, but you can already see by eye that the behavior is kind of changed in terms of separation and amplitude of the bursts. This is now a comparison in the same length of observation between the old and the new data. You see that the behavior has changed. Now, the fact that you don't see here an obvious burst doesn't mean that it didn't happen there. We are trying to quantify this and find whether there is a way to find evidence of events of QPEs that maybe they are barely popping up in the signal here. But it's not only about intrinsic faintness of the source, because for instance, this burst is brighter or as bright as the old one. So we'll see, but we are not too surprised because all the other QPEs have also changed behavior at some point. This is RxJ 1301. Johin showed the light curve of 2020. This is still unpublished. Margherita is publishing it. This is what this source is doing as of 2022. There's barely a recurrence time. Bursts may come in couples. And it's something that might relate to this source now. So you can have a diversity in amplitude and separations. And it's something that GSN has also started doing. GSN 69, Giovanni is going to present this tomorrow. When QPEs have reappeared, they have appeared with a different recurrence time and ratio between the amplitude. So the same source can undergo these changes. And now the question is, can you model it with your models? For instance, in Alessia's paper, switching on the frequency of the precession of the disk, you can depart from quasi-periodicity pretty easily, and you can produce these high ratios between amplitudes. Now, this is not a fit yet, but it's just a showcase that if you add precession of the disk, you produce something that looks like the data. Now, it's still early days, but it could be an answer for this complex behavior. I think that the eROQPEs have showed us is perhaps the only consistent properties across QPEs, which is the spectral evolution. This is a burst, count rate versus over time from blue to green, and this is hardness ratio versus count rate. So start of the burst, you get harder, you reach kind of the maximum temperature or hardness before the peak, which is here. Then you do this sort of hysteresis, and at the same flux, at the same count rate, the rise is always harder in the spectrum than the decay. And since we published this, we have checked in the other sources, and they all do the same. This is now GSN 69. Red to purple is the burst, red to purple in now temperature over luminosity, which is the same as hardness ratio in a way. And this is now eROQP 3 and 4. Here is the burst, start to end, dark to light. You have this nice hysteresis cycle in which at the same flux, the rise is always harder than the decay. This is the only, that I know of, the only consistent properties in X-rays across the QPEs, because the timing is all over the place. Sure, they repeat. Yeah, they repeat and they do this spectral evolution. That's what's common to all the QPEs. So whenever, I guess, which is relevant, whenever we want to find whether these events happen in other wavebands further out with other periods, we should check this spectral evolution to see whether it's consistent or not. It might be still an emery, but it might not be doing the burst with the same physical process as these QPEs. eROQP3, as I mentioned briefly, it showed a decay in the quiescence. This is now, forget about the bursts, the emission in quiescence called meters 1, 2, 3, 4, and 5, and detections, and a very deep upper limit coming from maximum Newton. We didn't detect the source in between the flares. It's 2 data points. really want to fit anything here. To be fair, this is not even a lot of plot, so this is all wrong. But anyway, the trying to kind of fit this data, you can't do it with one slope. It's just a point. It's a decay which is not one single power law, not one single exponential decay. It's some sort of decay. Let's put it this way. I don't want to constrain whether it's a full or partial or whatever.
That's the flux between the flares. You're plotting the flux between the flares.
The flux in quiescence between the flares as it evolves over time, and it has decayed in some way, which is not an exponential. That's what I'm saying. But it's still, you can call it whatever, TD, like decay in an informed way from the other sources, based on these two data points. I wouldn't tell you, oh yeah, it's got to be, right? There's nothing, the optical, nothing, this is just a decay in continuum in X-rays. But still, it's together with the other points of evidence that there might have been a TD here, I don't know. This is now adding the flares. Now, XMM has seen the burst, so this is definitely the peak. In eROSITA, we have a 40-second snapshot which caught the burst. So this is kind of a lower limit to the peak. So in a way, also the peak must have decayed. If these are lower limits, and this is definitely the peak, this was, for instance, 10 times brighter over 2 years. So also, like in GSN 69, the quiescence in the peak have decayed. eROQP4 is bringing something else in the mix. It's the first time that there is a transient harder component during the burst. Now I'll guide you through this plot. So this is the quiescence, which I had to model with also something in addition of the disk black body, faint component that I model with componentization. It's not necessarily componentization, it's also like a very soft spectrum. So I'm not sure, but whatever. Like it's just to tell you there's a harder component in quiescence. Now, this model here of the quiescence has been fixed throughout the burst, so this emission is accounted for during the burst, but still you see there's a big thermal component that dominates the QP peak, and yet there are counts in excess up to 8 kV for the first time during a QP flare. If you want to model this as a componentization of this component, it's still a softish power, or maybe more than 3. It's not really constrained, but there is definitely signal there. And I don't think we observed it before during the peak of a QP to this extent. Maybe we always kind of found some sort of excess counts around 2 kV compared to a thermal spectrum, but you can't really fit anything there. But this is for the first time something that pops up.
So are you saying that actually works if you Comptonize the QPE thermal part, you can actually get this excess during the flare? Have you done modeling of this, or are you just sort of suggesting?
I have modeled the spectrum with a componentization model of this component.
Yes.
I'm not necessarily claiming that it is such. It's just something that happens in accreting sources. I thought, yeah, rather than putting just a power law, which doesn't mean anything, I just put a componentization model.
I'm just trying to get at, is the QP have to make a power law in addition to the thermal part, or can that just come along for the ride if there's a quiescent?
It's I don't have this plot, but it only pops up. So if I show you this plot again, just to guide your eye, it only shows up here in these two spectra. It is a non-detected here, here, and here, the extra component. So it's transient. That's why I thought it probably pops up because of this component.
Okay.
But I meant this plot on Friday.
Okay, no, I'm just trying from the modelist standpoint, I'm trying to figure out if we still just have to explain something thermal. Thermal that then is being influenced by the fact that it's sitting near an accreting black hole.
It's a harder component that it's not seen in other sources. But one more point is that the luminosity ratio is about 100. So if this component, which is the case for the other source, is 10 to the 42, and this is 10 to the 40, we don't detect this. So it might be, in hindsight, that this component could have also been there in the other sources. It's just not detected because it's too faint. This is also, you don't constrain a spectrum with this signal here.
Right.
Kind of put a model and get a flux, essentially. And this is just to give you an idea, the soft X-ray luminosity. So 0.2, what you see here, the integral of what you see here, it's 10 to the 42 for this quiescence, a few 10 to the 40 for this power law, a few times higher for this other component. And obviously the soft X-ray is dominated by this. And I wanted to do the plot for the volumetrics. If you extrapolate to the full SD of each model. This model dominates because this is an accretion disk model which can go all the way down. So this is volumetrically dominant. This is perhaps just a just a black body component. So volumetrically, the questions is still as bright as the burst. I'm going through the summary. Sorry, Adam, for being a little late. Yeah, so we found 4 QPEs out of 6, confirmed one with eROSITA. So at the moment, it is the way to find them, but eROSITA has stopped, so this wasn't last for too long. As a community, we need to find more ways to find QPEs, but maybe that's an item for discussion for later. Just as a summary on what's new on the eROSITA QPEs, eROQP2 is basically the most regular one, because now also GSN has started doing something funky. And that's the one that, in principle, we should follow up for constraining the orbit better. I've tried for 2 years and failed, but I'll try again this fall with the XMM proposals, especially now that there are your nice models out, so they believe me. eROQP1 has become a little weirder. It's not something that wasn't seen before. Amplitudes have changed, recurrence times have changed. We are doing our best to dig this out of nicer data, which is very beautiful and powerful to get you like long baseline, but it's a little bit trickier to disentangle what's true signal in this data, and there's also work that Jane is putting into this. And eROQP3 has also showed a decay in the quiescence. At this meeting, we can probably call it TD-like, and nobody will be offended. eROQP4 has showed a harder component during the flares for the first time, and this is what's new from the eROSITA QPE.
Thank you for the great talk. I guess we do like a short 5-minute question time thing, and then
Sure, yeah.
and then make sure we have our coffee break on time, and then have a big discussion this afternoon. So,
Yeah, I have a question about E1. Because I'm curious to understand on what time scales is that change occurring? Because so you have a chunk of observations then in 2021, yeah.
Yes. So
Which is the one we use, I think.
I think I gave you the one in 2020. So this one.
Oh, 2020, okay.
This is 2021. There is 2022, which I didn't plot, which is a bit noisier, but still.
So you're saying that in a year,
Yeah.
the behavior is changed dramatically.
From
This is
this
a
to
year.
this, it's
Okay.
a year and a half tops.
Yeah.
Yeah, a year to a year and a half.
But do you,
And this is less. Like this is 2 months.
okay. But
Within 2 months.
you have observation, like pause in your observation.
Yeah.
Okay.
Still,
So
though,
you cannot-
the
you cannot
way this was designed, so there are kind of 5 data sets like this with the same length spaced logarithmically in 2 months. I simulated a pessimistic scatter from this data, and obviously it wasn't as pessimistic as this. And I claimed I could have fitted all these accounting for the gaps and to get a P dot and everything. I can't anymore, but just because this has gotten unpredictably worse in terms of data quality. But we are trying to dig in the noise, because at this point, even if you don't really fit the burst, but you can tell, okay, the event was here, even with an uncertainty of like half a day, I don't care. Like you can still put it in the feed and get constraints, which are worse than I thought, but you can still get constraints. If you can claim you know the number of events, you can place constraints. We have to get to that point yet. I don't think we can claim it by eye, but we'll try.
Just to follow up on that, was the NICE data taken during nighttime or daytime?
We still need to check that, because you think that the
Because like I said, I got Swift data around the same time. It looks normal.
Yeah,
I
but the
actually
point
have
is,
data
so
being
the-
taken like today, I just got an email as well. So I can check later.
Yeah.
Maybe tomorrow.
Yeah. That motivates us maybe to do these exercises with Swift next year potentially. But apart from that, you need to account for the gaps, you need still a lot of data. So these 3 days that we have with Swift, if that's the longest baseline we can have, it means that the spacing between these observations of 3 days has to be much shorter than these 30, 40 days that I could do at the end of this logarithmic space. So we can do the same exercise, but if we know for sure that the maximum baseline is 3-4 days, we need to have shorter gaps in between.
Yeah, but doing those randomly sampled 3 or 4 days, I see the same quality of bursts that we're seeing like.
Oh, yeah.
So if I randomly sample.
Yes, I remember, yeah, when we chat, yeah, that's encouraging because it means that we can clean this data eventually, yeah.
But also
proposing
maybe
now.
just to point out, because there's so many theaters here who probably have not used
Yeah.
nicer data. Those error bars that are shown on those are just measurement uncertainties, the systematic uncertainties that are not shown.
Yeah.
And NICER's background is not calculated at the same time as the data, it's an empirical background.
Yeah.
So it's based on data of blank skies taken from 5 years ago. So keep that in mind.
Yeah, it's not, you don't image the source and you don't image the background at the same time. You model the background and you assume that you know how it's behaving. And we know that we don't in NICER, that's the point. So it's really hard to clean NICER data. You didn't have to here.
Yeah.
We were all happy, but still here we're getting closer to this noise, so we have to now. Yeah.
So the top one I checked, that was taken during sunshine equals to 0, meaning nighttime.
Yeah.
The first observation was.
In 2020, yeah, we need to
best
check.
conditions
We need to check.
away from the sun.
I think the sun angle wasn't too bad. Oh, sorry. Well, we'll talk about this later. It's getting too technical.
So if I understand correctly, it may not be as messy
Yeah.
as it seems.
So yeah, so
Yeah.
that's something I think.
No, the intrinsic behavior could be cleaner for sure. Yeah.
Maybe it's
Okay,
not messy,
that's-
maybe it's still fine, is what I'm.
But still, keep in mind,
Good news for us.
the recurrence might be similar, but the amplitude, this can't, you can't fake it too much, right? You can kind of lose your power to find the burst closer to the noise, but the fact that they're now varying a lot, I mean, this stays the same. But this isn't too worrying because the other two sources are doing the same in terms of amplitude ratios.
Right.
The periodicity might be of the order of this one. It's a little bit more scatter, but changing the ratio of the amplitude makes the fainter bursts hardly detectable with S, and we have to work on that. Sorry.
No questions?
Yeah, you know,
I thought you had your hand up. Earlier.
I can see.
No. Oh, okay, sorry. I completely.
can I ask a quick question?
Yeah, go for it.
So Riccardo, you're showing this plot of the summary with the orbital decay idea, right? For E, yeah, that one. So just for thought experiment, does it make sense? We're not looking at, just dynamics. We're looking at dynamics convolved with radiation.
Mhm.
That's the stochasticity of emission, right? So does it make sense to directly apply 2-point sources going around model to X-ray data, which is, like I said, it's a combination of all these things that you see.
It is, but if the noise from the emission mechanism is mostly from the extra frequencies that might be in play, this is the cleanest you can get. So this is the easiest that you can get a orbital constraint for, because this doesn't probably have a precession of the disk. This doesn't have all the other complications. You only have to worry about your uncertainty in estimating the arrival time of the event and how to relate that to the orbital event. But if you get to the point in which they're basically, so we see that they're within the uncertainties, they got to be consistent for this short epoch. So it is a system that potentially can become regular in terms of arrival time of these events. And the fact of how delayed is the X-ray emission compared to the actual crossing, that's probably something for the theorists. And it probably can change from source to source. And even in the same source, I guess, if you have precession of the orbit and the inclination of these piercing changes. But we can quantify this, I guess, in a way that we can provide it to the proposal. We can work on this together if you want. Yeah.
That's what I would bring it up to the theorists to think.
Or is this?
I have a question, but I could also read it later. So if we want to stop, that's fine.
Yeah, okay, let's go for coffee and then.
Sounds good.
Phyllis, thanks, Ricky. Well,